4 out of 5 Canadians will experience back pain. Take a look around. That's an awful lot of us here today. Our spines work hard, giving us the freedom of movement we often take for granted, at least until that movement starts to hurt. The cause of back pain is not well understood, but the intervertebral discs are implicated in most cases. The discs are a soft tissue that separate the bony vertebrae, absorbing shock and allowing us to bend and twist. When damaged by age-related wear or trauma, there can be debilitating consequences. Right now, the only treatments are limited to pain management or invasive surgeries with poor outcomes. So why are these tissues so hard to treat? Well, cells drive the healing process. And compared to other tissues, the discs have relatively few cells, particularly at the center, which is gel-like, composed of a network of proteins and sugars called the extracellular matrix. It's here at the center that we see the greatest changes during degeneration. So my research asks, could the disc be restored by introducing healthy cells to the center in a protective scaffold that mimics the original healthy matrix? Such a scaffold needs to draw on water to form a gel, yet withstand repeated compression. It also needs to be injectable to protect the surrounding fragile tissues. To meet these criteria, I'm developing a tri-block polymer. A polymer is a large molecule made up of many repeating units. You can determine its properties by changing its repeating units. So mine has a strong core to resist compression, and each repeating unit has a water-soluble side chain, shown here in blue, to draw on water and form a gel. This polymer shows an exciting property that allows it to be injected. Consider making Jell-O. You can dissolve the powder in hot water, cool it down, and bang, you have a gel. My material does the opposite. It dissolves at room temperature, you can add in cells, you can inject it, and when it comes up to body temperature, it forms a gel. However, what I've been describing so far is a synthetic polymer, and cells don't really interact well with synthetic materials. So to ensure the cells can interact with the final scaffold, I'm attaching the polymer to a peptide, a small piece of a naturally occurring protein. In the next 2 years, I'll be investigating how the cells interact with the scaffold and how it holds up under repeated compression. Whether this is the solution to disc disease or not, it will help us to better understand these soft tissues that have challenged medicine and been a pain in our back for so long. Thank you.